This work is part of MFMET for establishing metrology standards in microfluidic devices, a European project financed by IMPIA. I am Thomas Daubjerg from DTI, and I will talk about flow in microfluidic devices. Flow is a very important quantity in microfluidics. And to introduce flow, I would like to present two examples of microfluidic applications that use flow. And these examples are in themselves quite complex, so one could talk for a long time about all the details of the applications and how they work, but we will not do that here. I will just give a very brief presentation and say that they exist and how there is microfluidic flow in them. So first on the right, we have the example of inkjet printing. And the idea here is that you have these bottles of an ink supply, and then you have a pump. So you generate a flow of ink that goes from the bottles into this inkjet nozzle. And then the nozzle propels droplets of ink. And there are some details with electric charge and electrostatic deflection plates, so you can actually steer these droplets of ink. And if you steer and target the correct locations, then you can make patterns. So for example, in this cartoon, the letter E is printed. So this is an example of a very useful printing technology, and in the example there is microfluidic flow. Now another example is here on the left, and that is continuous flow PCR, where PCR stands for polymerase chain reaction. And this is a method that is very useful for diagnosis of infectious diseases and DNA sequencing. And you might actually be familiar with some aspects of this method if you lived through the COVID-19 pandemic. For example, here there's an image showing a cotton swab taking a sample from a nose. And the idea in PCR is that you can have a small DNA sample, and then you can run it through the PCR method where there is this serpentine PCR channel. There are some details with some temperature cycles of the channel also. But as this small DNA sample and some substances goes through this system, what will happen is that there will be billions of copies made of selected DNA segments. So you can start with having a very, very small DNA sample, and then you can end up with having an amplified sample that is much, much greater and great enough to be used for some detection method, for example, capillary electrophoresis. So this is another example of a useful method where you have this microfluidic flow as a very important component in it. And I hope that this introduction got the message through that there are these very, very useful methods and technologies where microfluidic flow is a very important part of them. Flow quantities are used to describe flow in microfluidics. And this slide shows three examples of flow quantities. So first you have the volumetric flow rate, denoted by the symbol Q, and that describes the fluid volume passing in a channel per unit time. Then there's the pressure difference, denoted by the symbol tilde P, and that describes the difference in pressure between two locations along a microfluidic channel. And finally, we have the hydrodynamic resistance, denoted by the symbol R, and this describes the ratio of pressure difference and volumetric flow rate. And actually, the hydrodynamic resistance is a constant characteristic for a given microfluidic channel. And here you can see the definition of the hydrodynamic resistance written out as an equation. And also notice that hydrodynamic resistance has this property that if two channels are in series, then the combined hydrodynamic resistance will be the sum of the two channels' individual hydrodynamic resistances. In microfluidics, flow is typically realized with flow generators. So examples of flow generators could be pressure controllers or syringe pumps. And here you have a photograph of a syringe pump. So the idea here is that this machine has a block here, and the block can move, and as it is compressed, then the syringe that is right here will be compressed, and then a flow will leave the syringe. And then we could imagine the flow leaving the syringe and entering the tubing and going to some microfluidic device, in this example a microfluidic chip, and then the flow goes through one of these microchannels in the chip and exits on the other side. And such equipment exists that can give a precise control of flow in microfluidics. Other equipment that exist in microfluidics are different types of sensors. So for example, you can have flow sensors that can measure the flow, and you can have pressure sensors that can measure the pressure. Combining the previous quantities and concepts, we here present a laboratory method for determining the hydrodynamic resistance. And for convenience, the hydrodynamic resistance is repeated here. The laboratory system features several components. First, a syringe pump for generating the flow, then two sensors, one for measuring the flow and another for measuring the pressure. And the outlet of the system is at atmospheric pressure, so this pressure sensor actually measures the pressure difference from its location to the outlet of the system. And these two sensors measure matching values of flow and pressure. So their measurements can be used to calculate the hydrodynamic resistance. And the laboratory system is then used in two configurations. First, a configuration where it's only the system, so there's no device under test. And then you determine the hydrodynamic resistance of the system alone. Then there's another configuration where the system is used together with the device under test. In this example, it's a microfluidic chip. And then you determine the hydrodynamic resistance of the combination of the system and the device under test. Here we see results from measuring hydrodynamic resistance. So first, notice the figure on the left. It shows pressure versus flow. So in this figure, each data point is a matching pair of a flow measurement and a pressure measurement. And we see that the data falls into two groups. So the lower group here is the configuration of the laboratory system, where the system is alone without a microfluidic chip. And the upper group here is a configuration of the laboratory system where the system is used together with the channel of a microfluidic chip. And to this data, a linear equation was fitted, one for each data set. And we can see the parameters of these fits over here. And as the agreement between data and fit was quite well, we interpreted that the slope of these fits are the hydrodynamic resistances for each of these two situations. So the value here is the hydrodynamic resistance of the system alone, and the value seen here is the hydrodynamic resistance of the laboratory system together with a channel of a microfluidic chip. And remember this additivity property that was introduced for hydrodynamic resistance. So what you can do is that you can subtract the hydrodynamic resistance of the system, and then you are left with only the hydrodynamic resistance of the channel. So this is the hydrodynamic resistance of the channel that was tested alone. And if you do that, you get this value that is displayed here. And you can compare this value with an expected theoretical value from laminar flow theory. And in fact, the expected value is captured within the confidence interval of the determined value here. And we reached the end of the presentation. And to summarize, we saw that flow in microfluidics is an important quantity for useful applications. We were introduced to the flow quantities volumetric flow rate, pressure difference, and hydrodynamic resistance. We saw a laboratory system for measuring hydrodynamic resistance. And the determined value of hydrodynamic resistance agreed accurately with the expected theoretical value. In conclusion, the hydrodynamic resistance may be used as a quantitative parameter in characterization, quality control, and standardization of microfluidic technology. And I would like to thank all project partners for their contributions to MFMET. You can find more information in the links in the video description and on the project's website, mfmet.eu. Thank you for watching.